We live within a swirling disk made up of 400 billion stars. The Milky Way galaxy stretches 100,000 light-years from one end to the other. Sounds huge, right? But the part of the universe we can see goes across 93 billion light-years, and scientists think the universe itself might be endless. We're going to leave our galaxy and explore areas so vast, they make the Milky Way seem like a tiny grain of sand on a huge beach. Imagine standing in a field at midnight, looking up at a bright band across the sky. That's the Milky Way, our galaxy, as seen from inside. You're viewing the edge of a spinning disk in space, and everything you're seeing with your eyes is part of this galaxy. The Milky Way is about 100,000 light-years wide. Traveling across it at the speed of light would take 100,000 years. Scientists have measured this by studying variable stars called Cepheids, which pulse in brightness in a predictable way. Each pulse tells us exactly how far away the star is. Our galaxy holds between 100 billion and 400 billion stars. Each star is like a nuclear oven, many with planets of their own. Most of these stars are in a flat disk that's about 1,000 light-years thick. In the center, there's a bulge about 10,000 light-years across, filled with old red stars and a massive black hole weighing 4 million times our sun. We're about 27,000 light-years from the center. We're at the inner edge of the Orion Arm. We can't see the galaxy's full shape because dust and gas block the view. Astronomers map hydrogen clouds with radio telescopes and track star movements to figure out the structure. They found spiral arms wrapping around the core and a bar of stars cutting through the center. We live in a barred spiral galaxy, but that's not all. Simulations show dark matter surrounds the Milky Way in a huge halo, stretching nearly 2 million light-years out. This dark matter is like a gravitational skeleton holding our galaxy together. Without it, outer stars would drift away. We can't see this halo since dark matter doesn't emit light, but its gravity influences everything. Imagine our galaxy as an island in a dark ocean, 100,000 light-years of stars and gas within an invisible sphere 20 times bigger. That island feels vast until you realize the ocean stretches for distances, making our home a tiny speck. Right now, many smaller galaxies orbit the Milky Way, like moths around a light. The biggest of these, the Large Magellanic Cloud, is 32,000 light-years wide. Most are tiny dwarf galaxies, only about 500 light-years across. Our galaxy's gravity will eventually tear them apart. This has happened before, and will again. But if the Milky Way is just one island, how many others are out there in the ocean? This changes everything we know about our place in the universe. The observable universe is 93 billion light-years in diameter. Think about that number. Not 93,000 or 93 million, but 93 billion light-years from side to side, with Earth roughly in the center of what we can see. Comparing these numbers is mind-blowing. The Milky Way is 100,000 light-years wide, and the observable universe is 93 billion light-years wide. Divide those, and the observable universe is nearly 1 million times wider than our galaxy. If the Milky Way were the size of a quarter, the observable universe would stretch farther than from Earth to the Moon, and back then to the Moon again. Now it gets even stranger. We know light travels at about 186,000 miles per second, and nothing moves faster. The universe started expanding 13.8 billion years ago in what we call the Big Bang. You'd think light could only have traveled 13.8 billion light-years in any direction, making the universe 27 billion light-years across. But that doesn't consider one important thing. Space itself is expanding. As light travels toward us, the space behind it expands, pushing the source even farther away. Objects that emitted light 13.8 billion years ago are now roughly 46 billion light years away. Multiply by 2 to account for all directions, and the universe spans 93 billion light years. Measurements of cosmic microwave background radiation and distant galaxy redshift calculations confirm this. Picture this. If Earth shrank to a virus's size and that scale stayed consistent, the observable universe would be about the size of our solar system. The distance from here to beyond Pluto is like comparing a virus to the observable universe. That's the size gap between our world and everything we can detect. Each second, this universe grows. Light from farther away finally reaches us after traveling billions of years. The edge of our view expands by 3 light seconds per second, which equals 560,000 miles each second. We're watching the universe unfold in real time, but we'll never grasp its true size, as the observable universe is just the light that has had time to reach us. The actual universe stretches beyond what we can see, maybe infinitely. Every calculation and measurement shows one thing. We only see a tiny bit of what's out there. The Milky Way is unimaginably huge, but compared to the surrounding cosmos, it seems as small as a single cell in an ocean. And that ocean holds structures even more incredible than the spaces between them. 1 light year is 5.8 trillion miles. The distance light covers in 365 days at 186,000 miles per second. It would take a modern spacecraft around 70,000 years to travel just 1 light year. Light from Proxima Centauri, our closest star, takes 4.2 years to reach us. So, when you look through a telescope, you see how it looked 4.2 years ago. That light left the star before you even started reading the sentence. Astronomers call this looking back in time, and it's shown by every observation of distant objects. The Milky Way spans 100,000 light years across. Light from one side wouldn't reach the other side for 100,000 years. If people on opposite sides tried to chat, a reply would take 50,000 years to arrive. Entire civilizations could rise and fall in that time. Now, think bigger. The closest large galaxy, Andromeda, is 2.5 million light years away. The light we see from it left before humans walked upright on Earth. We're viewing ancient history when we gaze at the night sky, and the further we look, the more we peer into the past. The Virgo cluster of galaxies is 54 million light years away. Light from there started its journey before the asteroid hit Earth and wiped out the dinosaurs. The farthest known galaxies are over 13 billion light years away. Their light began traveling toward us when the universe was just 700 million years old, less than 5% of its current age. This makes for a strange reality. Astronomers don't study the universe as it is now. They study what existed billions of years ago. The further away something is, the younger it looks. The edge of what we can see shows us the universe, as it was 13.8 billion years ago, soon after the Big Bang. We'll never see what those areas look like today, since the light showing their current state won't reach us for billions more years. And here's a harsh truth. Space expands faster than light across extreme distances. Galaxies past a certain point are moving away quicker than light can travel, so their light will never reach us. They're beyond a horizon we can't cross, no matter how long we wait or how advanced our telescopes become. Every photon that reaches Earth has traveled incredibly far through space to get here. Light links us to the universe, but it also shows how separate we are. The Milky Way floats in a huge stretch of space where most galaxies will always be hidden from us. In this vastness, there are 2 trillion galaxies, according to years of study, but most of them are invisible to us. Our observable universe stretches to 46 billion light-years in all directions. This isn't a physical boundary you can see or touch. Instead, it's a horizon set by physics, proven through cosmic studies and looking at the cosmic microwave background. Light can only travel so far in a universe that's 13.8 billion years old. When you combine that with the universe expanding, there's a farthest point from where light could have reached us. Beyond that, galaxies exist, but their light hasn't arrived here yet. These galaxies beyond our view seem like they're in a different reality. Here's the tough part. The universe isn't just expanding, it's speeding up in its expansion. Dark energy, a mysterious force confirmed by looking at far-off supernova, is making space grow faster. This speeding up means galaxies near our visible edge are moving away from us as fast as light or even faster. Some have already crossed over to where they're moving faster than light itself. When galaxies get to this point, weird things occur. Their light could theoretically reach us, but as space stretches, it pulls the light into longer wavelengths. What started as visible light shifts to infrared, then radio waves, and finally to lengths too long for us to detect. The galaxy disappears from view, not because it stops shining, but space changes its light until we can't see it anymore. Scientists have figured there's a future limit, around 62 billion light-years. Galaxies further than this won't ever be part of our observable universe. Their light won't reach Earth because space grows too fast between them and us. We are surrounded by galaxies we can't ever see. It's not just distance keeping them from us, but the expanding space itself. This is an isolation deeper than just distance. About 90% of the galaxies we can see now will eventually fade away. As space expands, they'll shift to darkness. Future beings, if they exist, will only see galaxies in their immediate group. They'll see a universe that's seemingly small and almost empty. We live at a special time when the universe is old enough for complex structures to exist, yet young enough for us to spot distant galaxies. In about 100 billion years, most signs of the Big Bang will have stretched too far to detect. Future watchers might think they live in a quiet, unchanging universe with just a few nearby galaxies. But the true universe is much bigger than what we can see. Most guesses suggest it's at least 250 times larger. Some ideas say it's far bigger. One prediction places the entire universe at 10 trillion times our observable part, assuming it has an edge at all. Many scientists think space goes on forever, meaning the universe has no size, center, or boundary. We're just in one part of an endless space. The Milky Way is part of a known bubble that's 93 billion light-years wide, but that bubble might be less than 3% of the whole universe. The rest is beyond what we can ever reach or see. There are at least 2 trillion galaxies we know about, thanks to years of watching the skies, mainly with the Hubble Space Telescope, and using math to figure out the ones we can't see. Scientists confirmed this in 2016 by turning deep space pictures into 3D maps of galaxies. This count is 10 times more than the old guess of 200 billion galaxies, mostly because we've gotten better at spotting small, faint galaxies. Most galaxies aren't huge like the Milky Way. They are dwarf galaxies with only millions or billions of stars, rather than hundreds of billions. These smaller galaxies were common in the early universe and eventually joined to make bigger galaxies. But even saying there are 2 trillion might be too low. This number only includes galaxies we think we could see with today's or soon-to-be technology. About 90% of galaxies are still too dim and distant for us to detect. They're out of reach until we get better tools. The James Webb Space Telescope is starting to uncover some of these hidden galaxies, but many will stay unseen for a long time. Every galaxy has about 100 million stars on average. Some dwarf galaxies have fewer than 1,000 stars, while big elliptical galaxies can have over 100 trillion stars. Calculating these for 2 trillion galaxies gives a huge number. There might be around 700 sextillion stars in the observable universe. That's a 7 followed by 23 zeros, which is more than all the grains of sand on beaches and deserts on Earth. And these are just the stars we can guess at. Most stars probably have at least one planet too. If even part of those 2 trillion galaxies have 100 billion stars each, with most stars having planets, the number of planets is almost beyond comprehension. This vast number of galaxies doesn't float around randomly. They cluster together into groups, which form clusters, then superclusters, all aligned like threads or a web, separated by huge empty spaces. Astronomers call this the cosmic web, with galaxies lined up like lights along threads stretching across hundreds of millions of light years. Big, mostly empty bubbles of space lie between these threads, much bigger than the Milky Way. This setup matches what computer simulations predicted. Dark matter makes this cosmic web structure, with its gravity pulling regular matter into dense areas connected by strands. Galaxies appear where dark matter clusters. Voids are there because dark matter is thin in those regions, offering less material for gravity to act on. Here's the tough truth. Right now, we can see 2 trillion galaxies, but as the universe keeps expanding and galaxies speed away, more will slip out of view. Way down the line, people in the Milky Way will only see a few dozen galaxies close by that are gravitationally linked. Everything else will shift into invisibility. The universe is full of galaxies, each a separate island with billions or trillions of stars, and the Milky Way is just one of these 2 trillion islands. Most of these remain hidden in the vast darkness. Knowing there are other galaxies is one thing, but really understanding our connection to them is another. Our galaxy doesn't stand alone. It's part of bigger and bigger structures, each more complex than the last. The Milky Way we see at night isn't the whole picture. The stars and gas we see are just a small part of what our galaxy really is. Surrounding everything we know is a massive halo of dark matter that stretches almost 2 million light years from the center. Dark matter doesn't give off or take in light and doesn't interact with the electromagnetic stuff we can detect. Scientists know it's there because of its impact on gravity, which is clear and backed up by many observations. Stars on the outer edge of galaxies move quicker than expected if there was only visible matter. Invisible mass and gravity must be at play. Computer models show that dark matter halos around galaxies, like ours, spread way beyond the visible disk. Recent research backed this up by studying smaller galaxies moving around the Milky Way. These small galaxies move in ways that only make sense if a huge dark matter halo is pulling on them. By checking their speeds and paths, scientists figured out the halo is about 1.9 million light-years wide. This halo has more mass than all the stars, gas, and dust we can see in the galaxy. Around 85% of the Milky Way's overall mass is believed to be dark matter. The stars and planets and everything we can see make up less than 15% of the galaxy's gravity. We're living in a huge unseen structure, like insects crawling inside the unseen frame of a beast. The dark matter halo is thicker near the center and gets thinner towards the outer edges. Even at its far edges, about 1 million light-years from the center, the halo's gravity affects nearby tiny galaxies. Some of these small galaxies are slowly being pulled apart, with their stars drifting into the Milky Way's outer areas. This has happened before. Scientists have found streams of stars around our galaxy, the remains of small galaxies destroyed long ago. These star streams show the paths those galaxies took as they got pulled in. The Milky Way got bigger by consuming smaller neighbors, thanks in part to the dark matter halo that helped catch them. While the visible Milky Way is 100,000 light-years wide, the dark matter halo reaches almost 2 million light-years, making our galaxy 20 times wider than it seems. The Milky Way isn't just a single island in space. It's a huge invisible mountain with just a small visible top. This changes how we view galaxy size. When astronomers measure galaxies, they usually look at what they can see. But a galaxy's real reach goes far beyond what telescopes catch. Most big galaxies probably have dark matter halos like ours, which means they are much larger than they appear. Even with this big halo, the Milky Way is small compared to the next step up the cosmic ladder. Our galaxy is in a group, and this group joins with others to form something much bigger. To grasp this, we need to zoom out and see what our galaxy connects to. Andromeda is 2.5 million light-years away, and you can see it without a telescope on a clear night. That little smudge of light in Andromeda isn't a star or a cloud. You're looking at a galaxy with over 1 trillion stars, and each bit of light you're seeing traveled for 2.5 million years to reach you. Andromeda is bigger than the Milky Way. It's been measured, and its visible disk is about 220,000 light-years wide, more than twice the diameter of our galaxy. It has nearly twice as many stars as the Milky Way, and it probably has a similar mass. Andromeda is the main galaxy in our local group, and both galaxies orbit around a shared center of gravity. Its structure is similar to ours, as it's a spiral galaxy with a central bulge and arms that wrap around its center. A supermassive black hole is at its center, weighing 140 million times as much as our Sun. But Andromeda has a violent history. Astronomers found strange patterns in its star-filled disk, suggesting it swallowed several smaller galaxies a few billion years ago. Andromeda isn't sitting still. It's moving towards the Milky Way at about 250,000 miles per hour. Measurements of its motion show that in around 4 billion years, the two galaxies will collide. This won't be a gentle meeting. The collision will take hundreds of millions of years, with both galaxies passing through each other and gravity stretching stars into long tails. Eventually, they'll merge into a large elliptical galaxy. Stars don't usually crash into each other during these mergers because there's so much space between them. But the gravitational chaos will send some stars out into intergalactic space, while others will be pulled toward the new galaxy's core. Our solar system might end up farther out or even get completely tossed out. Simulations show there's a small chance we could be ejected from the new galaxy entirely, left drifting alone in the vast empty space. When this merger finally happens, neither the Milky Way nor Andromeda will be separate anymore. A new galaxy, sometimes called Milkomeda, will take their place. It will be bigger, heavier, and filled with new stars from gas clouds squeezed during the collision. Galaxies grow this way, by eating smaller neighbors and joining with others their size. But the Milky Way and Andromeda aren't alone. They're part of a group of about 50 galaxies, all held by gravity and orbiting a common center. This structure, confirmed through a lot of observations, is known as the local group. It spans about 10 million light-years across. The Milky Way and Andromeda are the biggest, with the Triangulum galaxy in third. The rest are mostly dwarf galaxies, each with less than 1 billion stars. These smaller galaxies orbit the big ones like moons around planets, caught by gravity and slowly heading toward eventual collisions. Every galaxy in the local group shares a common destiny. Gravity ties them together, and while the universe expands, pulling distant galaxies away, the local group stays together. The space between its members doesn't grow because their mutual gravity is stronger than the force causing universal expansion. We're stuck together, and long into the future, we'll combine into one giant galaxy surrounded by darkness. But the local group isn't alone. It's part of a much bigger structure, making even Andromeda seem small. 50 galaxies orbit through an area about 10 million light-years across. This is the local group, confirmed by decades of careful observing and measuring distances. The galaxies in this region are held together by gravity, creating a stable system that doesn't expand like the rest of the universe. The Milky Way is at one end of the local group, while Andromeda is at the other. The Triangulum galaxy, which is about 60,000 light-years across and has around 40 billion stars, is situated between them. These three big spiral galaxies make up most of the group's mass, but there are a lot more smaller galaxies around. There are at least 47 dwarf galaxies in the local group. Most of them orbit either the Milky Way or Andromeda. The large and small Magellanic Clouds orbit our galaxy and can be seen from the southern hemisphere as fuzzy lights. They are slowly being pulled apart, with their gas and stars forming streams that feed into the Milky Way. Andromeda has even more small galaxies circling it. More than a dozen are known, but there are likely many more that haven't been found yet. These tiny galaxies are hard to spot because they have few stars and don't give off much light. You need really sensitive equipment to see them against the glow of faraway galaxies. The local group didn't form all at once. Computer simulations show that small galaxies came first, soon after the Big Bang. Over billions of years, they came together to form larger galaxies. The Milky Way and Andromeda grew by consuming many smaller galaxies. The dwarf galaxies we see now are the ones that haven't merged yet, but most will eventually get absorbed. Gravity is what keeps the local group together, mostly because of dark matter. The stars we can see in all 50 galaxies make up only a small part of the total mass. Most of the mass is invisible dark matter spread out through the area, holding it all together. Without dark matter, the local group would have split apart a long time ago as space expanded. The center of mass for the local group is somewhere between the Milky Way and Andromeda. Both galaxies orbit this point, which is why they are slowly moving closer together. They are on gravitational paths that will eventually cause them to collide. It's not a matter of if, but when. As the universe expands, the distance between groups of galaxies increases. The local group will become more isolated. Already, the nearest galaxy groups are millions of light-years away. The Maffei group is around 10 million light-years away and is obscured by dust in the Milky Way. The Sculptor group is 11 million light-years away. These nearby groups are moving away as space expands. Eventually, the local group will merge into one big galaxy. Simulations predict that in 100 billion years, the Milky Way, Andromeda, Triangulum, and most dwarf galaxies will combine. From the outside, it would look like one large elliptical galaxy instead of 3 spirals. Inside, people might look out and see almost nothing, since nearby galaxies will have moved beyond the cosmic horizon. But for now, the local group is part of a bigger structure. We're near the edge of a huge collection of galaxy groups and clusters. It's like a big, flat disk of galaxies that makes the local group seem tiny. This structure is the main feature of our part of the universe. The Milky Way and Andromeda are heading toward each other, moving at about 250,000 miles per hour. This speed was confirmed by accurately measuring Andromeda's movement in the sky and its redshift as it gets closer. In about 4 billion years, give or take a few hundred million, a collision will happen. Picture watching this from outside both galaxies. At first, they slowly approach each other, still looking like spirals. As they get closer, gravity pulls out long streams of stars between them, creating light bridges in the empty space. The galaxies' shapes get distorted as they start to feel each other's gravitational pull, even from far away. Eventually, they touch, with the edges of their dark matter halos overlapping. Stars from one galaxy move through the other without hitting, because the space between stars is huge, making collisions unlikely during this clash. However, the gas clouds do collide. Massive hydrogen clouds crash into each other at high speeds, leading to compression and heating. This compression sets off bursts of star formation, lighting up both galaxies with newly formed stars. The first pass takes millions of years as the galaxies pass through each other, with their centers coming within tens of thousands of light years apart. Gravity twists them, changing the stars' paths. Some stars get enough speed to escape the galaxies altogether, heading out to wander in intergalactic space forever. Others move toward the center, where the two supermassive black holes start to interact. After the first pass, the galaxies separate but can't break free. Gravity pulls them back, and over the next few 100 million years, they circle their shared center and collide again. Each collision throws out more stars, creating long tidal tails that stretch hundreds of thousands of light years. These tails show where stars have been pulled away from their galaxies, left to drift in the space between. After several passes, the galaxies lose their spiral arms. The rotation that kept their arms organized falls apart, and stars start moving in random orbits, forming a spherical cloud instead of a disk. This is how elliptical galaxies are created. They come from major mergers and show the chaotic stellar paths as evidence of their violent pasts. Eventually, the two galactic cores merge. The supermassive black holes at their centers get closer, drawn by gravity and slowed down by dynamical friction. As they come near, they start orbiting each other, spinning faster as they lose energy to gravitational waves. We know this happens thanks to gravitational wave detections from merging black holes, though we haven't directly seen supermassive black holes come together. They spiral inward for millions of years. Finally, they merge in a massive event that releases more gravitational wave energy than all the galaxy's stars emit in light. The new merged black hole, which is hundreds of millions of times the mass of our Sun, sits at the center of the new elliptical galaxy. Our solar system should make it through. Direct star collisions are unlikely, but our spot in the galaxy may change. We might move farther away from the center or get pulled closer in. There's even a tiny chance of being ejected into intergalactic space during one of the wild passes. Once the merger is over, the night sky will change completely. Andromeda won't just be a faint spot. It will dominate the sky, taking up a large part as the galaxies merge. New stars will light up in huge star-forming areas. Eventually, the chaos will settle into a new, stable shape, forming what's called an elliptical galaxy, or Milky Way. This galaxy will hold all the stars from both the Milky Way and Andromeda, with more than 1 trillion stars altogether. Despite its size, Milky Way will just be another galaxy, among many in a much bigger system. About 54 million light-years away in the direction of the Virgo constellation, there's a huge cluster of galaxies known as the Virgo cluster. It has over 2,000 galaxies squeezed into an area about 15 million light-years wide. The center is dominated by large elliptical galaxies, with the biggest being Messier 87, a huge galaxy with a supermassive black hole that's 6.5 billion times the mass of our Sun. The Virgo cluster is not isolated. Around it are at least 100 other galaxy groups and clusters spread across a large, flat disk. This whole setup is called the Virgo supercluster, sometimes referred to as the local supercluster, since the local group is near its edge. The supercluster is about 110 million light-years across, confirmed by detailed maps of galaxy positions and movements. Our local group is far from the center, about 65 million light-years away from the Virgo cluster, sitting on the edge of this structure. From our position, the Virgo cluster's gravity pulls us, dragging the local group toward it at a few hundred miles per second. This process is known as the Virgo-centric flow, proven by accurate galaxy motion measurements. The shape of the Virgo supercluster is not round. It's a flattened ellipsoid, like a disk or pancake, with galaxies gathered along this disk and fewer above and below it. This shape came about from how the structure was formed. Dark matter was the first to collapse, creating a framework, and galaxies formed where dark matter was densest. Between these clusters of galaxies are vast, nearly empty regions called voids, spanning tens of millions of light-years with few galaxies. Together, the voids and clusters make up what's known as the cosmic web. Galaxies gather along the filaments, which mark the surfaces of enormous bubbles, while the voids are mostly empty insides of these bubbles. The Virgo supercluster's total mass is about equal to 100 billion Milky Way galaxies, including both visible and dark matter. Most of this mass is dark matter, spread throughout, forming a halo extending beyond visible galaxies. The visible stuff, the stars and gas we see, accounts for only about 15% of the total mass. Even with its massive size, the Virgo supercluster isn't held together as a single unit. The universe is expanding, pulling its outer areas apart. Only the densest parts, like the Virgo cluster itself, are compact enough to resist this expansion. The rest of the supercluster will eventually spread out over billions of years as space expands between galaxy groups. This discovery, made in recent years, was surprising. Astronomers used to think superclusters were tightly bound, much like larger versions of galaxy clusters, but careful measurements showed this isn't true. The Virgo supercluster is not stable. It's a temporary bunching of galaxies in our current time. In the distant future, it won't even be identifiable as a separate structure. This temporary configuration is just a small part of a much bigger picture. New observations have shown that the Virgo supercluster belongs to an even larger group of galaxies that makes it look small by comparison. The Virgo supercluster is massive, with as much matter as 100 billion Milky Way galaxies. Picture that. 100 billion versions of our galaxy, packed into a single area that's 110 million light-years wide. Now, each Milky Way galaxy might have up to 400 billion stars. Multiply those 100 billion galaxies by 400 billion stars each, and you end up with a number so huge it's hard to grasp. About 40 sextillion stars. That's a 40 with 21 zeros after it. More stars than grains of sand on all the beaches on Earth. But these numbers mostly come from calculations, not actually counting the stars. Many are too far and faint to see. Instead, astronomers figure out the total mass by looking at galaxy movements. How fast these galaxies move shows the gravity at play. More mass means more gravity, which results in faster movements. When scientists study these movements, They find that the visible matter in the supercluster only makes up a small part of the total mass. Dark matter, which doesn't emit light, makes up about 85% of it. This dark matter surrounds and fills the supercluster, affecting the paths of galaxies with its gravity. The Virgo supercluster's mass is unevenly spread out. At the center, the Virgo cluster holds a huge amount of mass, about 10 to the 14th times that of our Sun. This center pulls other galaxy groups in, creating a flow that drags our local group toward it at hundreds of miles per second. If we could see dark matter, we might see a vast web with galaxies as bright spots where the web strands cross, and dark matter filaments connecting them. Empty spaces would look like big bubbles, marked by galaxy-filled strands. But the Virgo supercluster isn't the largest structure. In 2014, astronomers discovered something bigger, changing how we understand our place in the universe. By studying galaxy movement, they found that the Virgo supercluster is just one part of an even larger structure, with about 100,000 galaxies, including the Milky Way, Andromeda, and the whole Virgo supercluster. This larger structure stretches 520 million light-years across, making it one of the biggest known. Its mass is estimated to be equal to 100,000 Milky Way galaxies, although estimates can vary. This discovery came from mapping galaxy paths, not just their positions in space. Galaxies don't move randomly. They head toward mass concentrations due to gravity. By tracing these paths back, astronomers found the gravitational area holding our region of the universe together. This large structure has a center where everything nearby is drawn. The Virgo cluster, our local group, and many others are moving toward it. This gravitational center, known as the Great Attractor, is a big mystery in astronomy. Something huge is pulling our galaxy, the Milky Way, the local group, and the entire Virgo supercluster, all moving the same way at over 1 million miles per hour. Scientists call this place the Great Attractor, which has been one of the most puzzling mysteries in space research for decades. The proof for this movement came from looking at the cosmic microwave background, which is the faint leftover radiation from the Big Bang. If we weren't moving relative to the universe, this radiation would look the same in every direction. But measurements showed that the radiation is slightly warmer in one direction and cooler in the opposite direction, showing a dipole pattern. This means we're moving through space, and this movement causes a Doppler shift in the background radiation. Astronomers figured out how fast and in which direction we're moving. The whole local supercluster is being pulled toward a spot about 250 million light-years away, towards the constellations Hydra and Centaurus. The gravitational pull needed for this must come from a huge mass, like tens of thousands of Milky Way galaxies in one area. However, our view in that direction is blocked by the Milky Way. Dust and stars from our galaxy block the light from that area in space, creating something astronomers call the zone of avoidance. Early efforts to directly observe the Great Attractor didn't show much. A few galaxy clusters were found, but not enough mass to explain the movement we see. Eventually, radio and X-ray observations were able to see past the dust. They found several massive galaxy clusters there, like the Norma cluster and the Centaurus cluster. These clusters have enough mass to explain some of the gravitational pull, but not all of it. It turns out the Great Attractor is more spread out than just a single cluster, covering a larger space. The mystery got more complicated when astronomers discovered the movement doesn't stop at the Great Attractor. The Great Attractor is moving too, pulled by an even bigger mass farther away. This next structure is called the Shapley supercluster, which is 650 million light-years away and contains over 8,000 galaxies. It's one of the most massive structures we can observe in the universe, and its gravity affects galaxy movements over huge distances. Discovering these massive structures helped scientists understand things better. Galaxies don't just move around randomly. They follow paths set by where matter, both visible and invisible, is found. These paths come together in dense areas and spread out from emptier voids. By mapping out these movements, astronomers can figure out where mass is, even when it's hard to see directly. In 2014, this way of mapping showed that the Great Attractor isn't a single mass by itself. It's the center of a huge structure containing the Virgo supercluster, the Hydro-Centaurus region, and other superclusters. This larger structure has been proven by many separate studies of galaxy speeds and positions. The Great Attractor area is the gravitational center of this big region, and everything within 520 million light-years is being pulled toward it by all the mass there. The Virgo supercluster, which once seemed like the main feature in our corner of the universe, is just one part of this bigger system. This finding made scientists rethink what makes a distinct structure. The Virgo supercluster isn't gravitationally bound and will break up over time. But the larger structure it's part of might be a true dynamic system, at least for now. This big structure has a name given by the astronomers who mapped it out. They called it Laniakea, which is Hawaiian for immense heaven or open skies. Confirmed in 2014, the Laniakea supercluster stretches about 520 million light-years across, identified through detailed mapping of galaxy movements. It has around 100,000 galaxies, including ours, all moving toward a common gravitational center. This represents our cosmic address on the largest mapped scales. Earth is in the solar system, which orbits within the Milky Way, part of the local group, near the edge of the Virgo supercluster, one section of Laniakea. Each level in this hierarchy increases in size by millions or billions. Laniakea isn't a single compact object. It's a vast web of interconnected filaments and nodes, where galaxies are mostly found along threads outlining large voids. The structure looks like a biological system, with galaxy arteries feeding into larger concentrations. The Virgo supercluster is a major branch, and the Hydro-Centaurus region is another. Several other superclusters add more mass. Laniakea's total mass is about 100 quadrillion times that of our Sun, a number with 17 zeros. This includes all galaxies, gas clouds, and dark matter, with dark matter being the main component, creating an invisible framework that holds it all together. Galaxies in Laniakea move in organized patterns, flowing toward denser regions instead of spreading out evenly. These movements follow the dark matter layout. Where dark matter is thick, galaxies move inward, while where it's thin, they drift into empty areas. Laniakea's border isn't a physical edge, but the limit of its gravitational pull. Beyond it, galaxies are attracted to other gravitational centers. The neighboring area is part of the Perseus-Pisces supercluster, which pulls on galaxies in its zone. Between these regions, galaxy paths get uncertain. Laniakea itself isn't gravitationally bound. Studies show that the universe's expansion is pulling it apart faster than gravity can hold it together. So over billions of years, it will spread out. Only the densest parts might stay connected. This brings up the question of whether Laniakea should actually be called a supercluster, since traditional definitions require them to be gravitationally bound. Laniakea isn't, so it's more a temporary gathering of galaxies with a shared motion for now. In the future, we'll likely see these galaxies spread over larger distances. Despite being temporary, Laniakea marks our place in the universe on a vast scale. Beyond it lie other structures, other galaxy basins headed for their own centers. The universe on this scale is like an ocean with many currents, each with billions of galaxies. Laniakia's discovery changed astronomers' views on cosmic structures. Instead of defining structures by appearance, we now look at their dynamics. A supercluster isn't just nearby galaxy clusters. It's a space region with a shared gravitational link. This dynamic perspective shows patterns that traditional studies miss. The cosmic web becomes visible when mapping galaxy speeds. Filaments show where matter flows along dense threads, and voids are where galaxies speed away from less dense areas. At filament crossings, huge galaxy groups form nodes anchoring the web. But even this cosmic web is only what we can observe. The universe stretches beyond our sight, maybe infinitely, with structure continuing beyond Laniakea, forming patterns we're just starting to grasp. The universe isn't random. Galaxies aren't scattered evenly, but arranged in a complex network of filaments and sheets, with vast voids between them. The pattern seen over decades of galaxy surveys is called the cosmic web, which is the largest structure in the universe. It developed from tiny density differences in the early universe, soon after the Big Bang. Back then, matter was spread out almost evenly, but there were small variations in density. These variations, seen in the cosmic microwave background, acted as starting points for forming structures. Gravity made these variations grow. Areas that were a bit denser than average pulled in more matter and became even denser. Areas that were less dense lost matter to nearby areas, forming voids. Over billions of years, this led to a variety of structures. Small groups combined to create larger ones. Galaxies formed where dark matter built up. These galaxies grouped into clusters and even superclusters, all shaping around the dark matter. This created a web of filaments. These filaments stretch hundreds of millions of light years long, but are only a few million light years thick. Galaxies cluster along these filaments like beads on a string. Where several filaments meet, large galaxy clusters form. Some clusters contain thousands of galaxies, within areas tens of millions of light years wide. In between the filaments, there are voids, which are large bubbles of almost empty space, usually 50 to 100 million light years wide. Some voids can be 300 million light years across. They have very few galaxies, mostly small dwarf ones. Although not entirely empty, they have some dark matter and gas, but their density is much lower than average. The cosmic web isn't fixed. It changes as the universe expands. Filaments get longer and thinner, while voids grow larger. Galaxies in the filaments slowly move towards the nearest cluster due to gravity. As time passes, the difference between dense and empty areas becomes more pronounced. Dense areas gain more mass, while empty areas lose more. Computer models simulate this structure well. These models start with dark matter, based on the density variations seen in the cosmic microwave background, and move them forward in time using gravity. The outcome aligns with what surveys show. Filaments and voids form, and clusters appear at intersections. The cosmic web naturally arises from gravity, acting on slightly uneven starting points. Observations support these simulations. Large-scale surveys, like the Sloan Digital Sky Survey, have mapped millions of galaxies across much of the sky. This data has revealed the cosmic web in great detail, showing filaments, voids, and superclusters along the filaments. The universe has clear structure on scales nearing 1 billion light years. The cosmic web is shaped by dark matter. The stars and gas we see follow where the dark matter goes. Dark matter filaments formed first, and galaxies came together within them later. This is why galaxies map out the cosmic web. They highlight where dark matter is concentrated, but the cosmic web itself is part of an even larger arrangement. The filaments aren't endless. They have specific lengths and gaps. An average size of about 300 million light-years represents the usual size of structures that formed from early density differences. Smaller differences led to smaller structures, while larger ones created bigger structures. The peak in the power spectrum of these fluctuations corresponds to structures around this size. The cosmic web spans the entire observable universe. No matter which way we look, the same pattern of filaments and voids is visible. Clusters and superclusters are part of the universe's structure. This uniformity shows that the same physical processes that created the cosmic web worked everywhere in the same way, supporting the idea that the universe is uniform at the largest scales. But between these filaments in the wide, empty areas, there's something that we find puzzling. These empty zones are the largest known structures in the universe. For instance, the Boötes void is 330 million light-years across, yet astronomers have only found about 60 galaxies there. In any typical space that size, you'd expect to find around 10,000 galaxies. This means the void is about 99% empty compared to the cosmic average. Voids take up most of the universe's volume, while filaments and clusters, which contain most galaxies, only use a small part of the total space. If you picked a random spot in space, you'd probably land in a void, hundreds of millions of light-years from the nearest galaxy cluster. The Boötes void isn't alone. Surveys have found dozens like it. The Sculptor void and the Eridanus supervoid are similarly vast, with the latter nearly 1 billion light-years across, one of the largest known structures. These voids aren't completely empty, though. They have some dark matter and gas and a few scattered galaxies inside them, but their density is far below average. How do voids form? They come from the same process that creates filaments and clusters, just in reverse. Regions that started slightly less dense than others after the Big Bang lost matter to their surroundings. As denser areas pulled in material, these sparse regions lost more and more, with gravity emptying them out over billions of years. This process is supported by simulations that show voids forming naturally as matter evolves under gravity. Inside these voids, the universe expands a bit faster than usual because there's less mass to slow it down. This causes galaxies near the edges of voids to move away from the center. Over time, this movement pushes the few remaining galaxies toward the void's edges, making their centers even emptier. The galaxies inside voids are different from those in dense areas. They're often younger and have more active star formation. This makes sense because in clusters, galaxies frequently collide and merge, using up their gas and stopping star formation. In voids, galaxies stay isolated, keeping their gas longer and continuing star formation at a regular pace. Voids also impact the cosmic microwave background. Light from the early universe travels through voids to reach us. As photons fall into a void, they gain energy, but as they climb back out, they lose energy. If the void stayed the same size, these effects would cancel out. But since the universe expands, voids grow while photons are passing through. Thus, photons lose more energy climbing out than they gained falling in, creating a cold spot in the cosmic microwave background, like a shadow left by the void. There's a cold spot in the direction of the Eridanus supervoid, and studies show the temperature there is slightly lower than its surroundings. This temperature drop matches what we expect if a supervoid is along the path of the light. This is more evidence for the void's existence beyond just the missing galaxies. Voids are challenging for some cosmological theories. The largest voids are at the edge of what standard theories predict. If structures form that are way bigger than expected, it suggests something unusual occurred during the universe's early stages. Most voids align with predictions, but the biggest ones challenge these limits. The existence of voids also raises philosophical questions. If most of the universe is nearly empty, what do we mean when we say the universe is full of matter? Matter seems to concentrate in small areas and connect like foam on water. While most of space holds almost nothing, we live in one of the rare crowded parts of the universe, on a planet in a galaxy that's part of a larger structure. Most of the cosmos is quiet and dark. Even the biggest empty spaces are small compared to what we can see of the universe, and these gaps are part of an even bigger structure that we can't fully grasp yet. The cosmic web stretches as far as we can observe and keeps going beyond what we can see, To understand how it's all held together, we need to know about the unseen framework that supports it. About 85% of the universe's matter is invisible. It doesn't give off light, absorb it, or interact with electromagnetic radiation in any detectable way. Still, it makes up most of the universe's mass, and without it, nothing we see could exist. Astronomers call this dark matter, and they've proven it's real through various facts. The first clue was from the way galaxies spin. Stars on the outer edges of spiral galaxies move faster than expected, if only the visible matter existed. Newton's laws say things farther from the center of mass should move slower, but these stars keep up their speed. This means there's more unseen mass beyond the visible parts that keeps them moving quickly. More proof came from galaxy clusters. The galaxies in these clusters move too fast to be held together by only visible matter. They should break apart, unless there's extra mass providing more gravity. Observations of hot gas in clusters support this. The temperature and spread of this gas show there's much more mass than just the stars and gas we see. Watching how light bends confirmed this further. Light from distant galaxies bends as it passes by massive objects, and the bending amount shows all the mass in the way, even if it's not visible. These observations highlight that galaxy clusters bend light more than just visible matter can explain. Maps of these effects reveal halos of dark matter around and within clusters. Dark matter forms the backbone of the cosmic web. Computer models using only dark matter create structures similar to what we see. These models start with small density changes. Dark matter particles gather into lines and points due to gravity. Where dark matter gathers, it creates gravitational wells. Ordinary matter falls into these wells, forming galaxies. The visible universe shows where dark matter is distributed. What is dark matter? We don't know yet. It must interact through gravity, but not electromagnetically. Such particles don't exist in our current physics models, suggesting dark matter is something new we haven't discovered in labs. Possible candidates include weakly interacting massive particles, axions, or even primordial black holes. Scientists worldwide are searching for direct proof, but dark matter remains hard to find. Even without knowing what it is, we can figure out where dark matter is. The bending of light maps out dark matter spread in galaxy clusters. These maps show dark matter is clustered where galaxies are but stretches farther. Dark matter halos around clusters are tens of millions of light years across, much bigger than visible galaxies. On bigger scales, dark matter shapes the cosmic web. The filaments are mostly dark matter, with galaxies marking their spots. Voids are areas with less dark matter. The universe's biggest structures follow the dark matter layout. Visible matter just traces this larger, invisible mass. Dark energy is different from dark matter. Dark energy is an even bigger mystery. It's a part of space itself that causes the universe to keep expanding faster. While dark matter provides the gravity to pull stuff together, dark energy pushes it apart. Dark matter helps form structure, but dark energy tears it down. The balance between these two unseen forces decides the universe's fate. Right now, scientists think dark energy makes up about 68% of the universe's total energy. Dark matter comes in at about 27%. All the normal matter that we can see and touch is only about 5%. Most of the universe is made up of things we don't really understand. This invisible framework is spread out all through the observable universe. Filaments of dark matter connect everything, while dark energy fills every bit of space. Together, they shape the universe from single galaxies to the biggest groups of galaxies. Everything we see today is because of their effect. Even with dark matter and dark energy ruling the universe, there are visible structures that overwhelm the size of the Milky Way by amounts that seem unbelievable. IC 1101 is over 1 billion light-years away, so far that its light has been traveling for over 1 billion years to reach us. It's the largest known galaxy, an enormous elliptical galaxy stretching about 4 million light-years across. That's 40 times wider than our Milky Way's visible disk, and even twice as wide when you count our dark matter halo. This galaxy has over 100 trillion stars, which is more than 200 times the number of stars in the Milky Way. If each star in IC 1101 had a planet, and each planet had a moon, the total number of worlds would still be mind-boggling. The mass of this galaxy is about 100 trillion times the mass of our Sun, making it one of the heaviest single galaxies known. IC 1101 didn't evolve on its own. It grew by consuming other galaxies over billions of years. Galaxies like these are believed to form from large mergers. When two spiral galaxies crash together, their orderly rotation gets destroyed. The merger scrambles the stars' paths, turning everything into a big sphere instead of a flat disk. Repeated mergers have created galaxies like IC 1101, which has probably gone through countless collisions like this. In the center of this galaxy is a supermassive black hole weighing around 66 billion times the mass of our Sun. This is one of the heaviest black holes ever found. For context, the black hole at the middle of the Milky Way is just 4 million times the mass of our Sun. The black hole in IC 1101 is 16,000 times heavier. Its gravity affects an area thousands of light-years across, controlling the heart of the galaxy. IC 1101 is located near the center of the Abell 2029 galaxy cluster, one of the richest clusters we can see. IC 1101's spot at the cluster's center isn't by chance. The biggest galaxies usually end up in the centers of clusters because they sink to the bottom of a gravitational well through a process known as dynamical friction. As IC 1101 moves through the cluster, it interacts gravitationally with surrounding galaxies, slowly losing energy and drifting toward the center. The night sky from IC 1101 would look pretty strange. In the outer parts of the galaxy, the stars are so far apart that the sky would seem darker than ours, with just faint points of light from distant galaxies. But closer to the center, the sky would be very bright. Stars pack closely in this region, creating a glow that could cast shadows from light years away. IC 1101 is an extreme example, but it's not alone. Other supergiant elliptical galaxies are scattered throughout the universe. Messier 87 in the Virgo cluster is smaller than IC 1101, but still makes our Milky Way look tiny. These giant objects sit at the center of huge galaxy clusters, and have become large by gobbling up other galaxies. Seeing big galaxies like these helps us understand how the universe developed its structure. Galaxies get bigger by merging and gathering material. Small galaxies were the first to form right after the Big Bang and have been combining into larger ones over billions of years, a process that still happens today. The galaxy IC 1101 keeps getting bigger by slowly pulling in small galaxies that drift nearby. However, not all galaxies are gigantic, like IC 1101. There are billions of tiny dwarf galaxies that are so small and dim that many remain unseen in most space surveys. These small galaxies greatly outnumber the giant ones, showing us a different part of the universe's structure. Most galaxies have fewer than 1 billion stars, meaning dwarfs outnumber large ones like the Milky Way by hundreds or thousands to one. The small Magellanic Cloud, visible in Earth's southern hemisphere, has only a few billion stars and is about 7,000 light-years wide. But even this relatively bright dwarf is at the large end of what dwarfs can be. The faintest ones found only have a few thousand stars, spreading across just a few hundred light-years. These ultra-faint dwarfs give off so little light that they weren't noticed until advanced telescopes in recent surveys revealed them. The Segue 1 dwarf galaxy, which orbits the Milky Way, has around 1,000 stars. From inside, it would look like only a few scattered dots against the night, barely enough to be considered a galaxy. Dwarf galaxies pose a challenge. Based on cosmological models, we should see many more small dark matter halos than the number of dwarf galaxies we actually find. Predictions say thousands of small halos should be around large galaxies like ours, but we only see a few dozen dwarfs. This issue, called the missing satellites problem, implies that either there's something missing in our models, or many dwarf galaxies are just too dim to see. Recent surveys lean towards the second idea. New ultra-faint dwarfs keep popping up around the Milky Way and Andromeda through advanced telescope discoveries. Every time we look harder, we find more. The findings suggest there are thousands of nearby dwarf galaxies, mostly invisible with our current technology. When newer telescopes arrive, we'll probably find even more. Dwarf galaxies have been the most common throughout cosmic history. Shortly after the first stars formed, small galaxies appeared all over the place. These early galaxies had only a few million stars each, but there were lots of them. Over time, they have merged into bigger structures. The dwarfs we see now are survivors, still around because they haven't merged yet, but many will eventually do so. Dwarf galaxies are more dominated by dark matter than larger ones. Some ultra-faint dwarfs have a mass-to-light ratio of over 1,000, meaning they contain 1,000 times more dark matter compared to stars. They're practically dark matter blobs, with some stars sprinkled in. If it weren't for dark matter, these galaxies wouldn't have enough gravity, and their stars would drift off into space. Dwarf galaxies show the smallest scale of galaxy formation. Below a certain mass in dark matter, galaxies just can't form. The smallest dark matter halos can't hold onto gas or bring it together. Starlight and cosmic radiation heat the gas, stopping it from cooling and turning into stars. Only halos above a certain mass threshold can make visible galaxies. This is why we don't see anything smaller than these ultra-faint dwarfs. The physics of cooling gas and star making sets a minimum size. Dark matter halos are out there, but they don't have stars and stay invisible, only showing up because of how they affect things we can see. If you added up all the dwarf galaxies, their mass might be more than the big giant galaxies. Dwarf galaxies are small individually, but lots of them are out there. If you totaled the star mass in all the dwarf galaxies we can observe, It might be as much or more than giant galaxies like ours. Most galaxies are small, even though big ones are few. Dwarf galaxies are everywhere, but they don't matter much when compared to what decides the universe's future. The universe isn't just getting bigger, it's doing so faster. This was found out in 1998 by looking at far-off supernovae, surprising scientists. It was thought that gravity should be slowing down the expansion, but instead, galaxies are moving away more quickly. This was discovered with Type 1a supernovae, which are exploding white dwarf stars that help measure cosmic distances. These supernovae shine at a consistent brightness, letting us measure distances by how bright they look. When astronomers compared these distances with redshifts, they saw different expansion speeds over time. Distant supernovae looked dimmer than expected, meaning they're further than they should be if the rate of expansion was steady or slowing down. The only reason is that expansion has sped up since these supernovae went off billions of years ago. Space itself is stretching more now than before. This needs something new that pushes rather than pulls. This force is called dark energy, making up about 68% of the universe's energy density. Dark energy doesn't clump and pull like dark matter. It spreads out across space and pushes things apart. We don't really know what dark energy is. The basic idea is that it's the energy of empty space, sometimes called vacuum energy, or the cosmological constant. Quantum field theory says all empty space should have energy, but the numbers don't match what we see. This mismatch, known as the cosmological constant problem, is a big unsolved issue in physics. Whatever dark energy is, its impact is easy to see. It makes the universe expand faster. In the early universe, when it was smaller and more tightly packed, dark energy didn't matter much compared to matter. Gravity ruled, slowing things down. But as the universe grew, dark energy became more important. About 5 billion years ago, as shown by various independent checks, dark energy's pushing power surpassed gravity's pull, making expansion speed up, which changes the universe's future. Structures not held together by gravity will be pulled apart. Galaxy clusters will stick together because their inner gravity is strong enough to hold on, but superclusters will break apart. The cosmic web will stretch until it snaps. Eventually, even groups of galaxies might split up, leaving each galaxy on its own. The Milky Way and Andromeda will still come together because their gravity is strong enough, and they are near enough that dark energy can't stop them. However, galaxies farther out are already moving beyond our grasp. The light they send won't reach us because space is expanding too quickly. They are moving past the cosmic edge, disappearing from the universe we can observe forever. In the distant future, people in our combined galaxy will look out into space and see almost nothing. Nearby galaxies beyond our local group will have drifted so far away, we won't be able to see them anymore. The cosmic microwave background will fade until it's undetectable. Space will look empty and dark. Future societies might think they're alone in an unchanging universe, not knowing that billions of galaxies once filled the sky. Dark energy also shapes space itself. Studies of the cosmic microwave background and galaxy arrangements show that the universe is mostly flat because of dark energy. If the force of dark energy was different, the universe might be curved in ways that would prevent large structures from forming. This acceleration limits what we can see. Some galaxies will always remain out of sight, as their light will never reach us. These galaxies are beyond the cosmic horizon, in parts of space that will always be separated from us. This brings up a question astronomers have wondered about since Edwin Hubble realized the universe was expanding. If galaxies that are too far won't ever be reachable, what marks the edge of what we can see? It's 46 billion light-years away. That's where the observable universe stops in any direction from Earth. Beyond that, nothing can be seen. Light from farther away hasn't reached us since the Big Bang, and never will, because of the expansion. This creates a spherical boundary around us, known as the particle horizon. Everything inside can potentially be seen. Everything outside stays permanently invisible. This boundary isn't a physical wall, but is because the universe has a finite age, and light has a finite speed. The cosmic horizon moves over time. As the universe ages, light from more distant areas finally makes it to us. Every second, the part of the universe we can see grows. New galaxies show up at the edge of visibility as their ancient light finally finishes its trip across space. But there's a limit to this growth. Because of the universe's acceleration, there's a maximum distance light can travel to reach us, no matter how long we wait. This defines another boundary, called the cosmic event horizon. It's roughly 62 billion light-years away, confirmed by cosmological calculations. Galaxies beyond this point are moving away faster than the speed at which light can reach us. Their light will never get to us. This creates an unusual situation. We can see galaxies now beyond this event horizon because we're seeing light they sent out billions of years ago when they were closer. But we'll never know what they look like now or in the future. These galaxies have crossed into an area of space that we can't connect with anymore. From those distant galaxies' point of view, we've crossed their event horizon. People there can see our galaxy as it was billions of years ago, but they'll never catch our future light. We exist in their past, and they exist in ours, but not in each other's future. The expanding space has cut off our connection. The horizon creates a barrier more absolute than just distance. Even if we traveled at the speed of light, we couldn't reach galaxies beyond the event horizon. Space between us is expanding faster than we could travel. Trying to reach them would be like running on a treadmill that speeds up faster than you can run. You'd never get closer to where you're going. This brings up deep questions about existence. Do galaxies beyond our horizon truly exist if we can't interact with them or receive information from them? Physics says they do. The laws of nature remain the same at the horizon. Space goes on beyond what we can see, but we can't confirm this by looking. The horizon limits how we understand the universe, since we can only study a limited area. If the universe is endless, we're viewing just a tiny part of it. Our area's quirks could give us the wrong idea about the rest. Laws we think are universal might only apply here in our observable area. The cosmic microwave background measurements help reassure us since the radiation looks uniform, suggesting the universe is similar on a large scale. If our area was unusual, we'd see bigger differences. This uniformity implies that what we see is statistically representative, though the horizon limits our knowledge. The size and shape of the universe and what's beyond what we can see might not be knowable. We can make guesses and theories, but can't observe them directly. The universe goes beyond what we can reach, maybe forever, and we can only explore the small part available to us. This part has around 2 trillion galaxies spread across 93 billion light-years. It's a huge sample, but might just be a tiny piece of reality. Most of the universe is beyond the horizon, and we can't know it. We see about 3% of it. This estimate arises from comparing the observable universe's size with theoretical calculations of the whole cosmos. If cosmic inflation happened as expected, the full universe should be way bigger than what we see. Cosmic inflation refers to a brief period when space expanded extremely fast, right after the universe began. During this rapid growth, the universe stretched from subatomic sizes to much larger than the observable section. Observations of the cosmic microwave background support the idea that inflation happened, shown by the temperature patterns in the sky. If the universe expanded by at least 60 times this rapid growth period, as many models suggest, the size would be huge. An E-fold means making the size about 2.7 times bigger. 60 E-folds mean multiplying by that number 60 times. This results in a universe at least 10 to the power of 26 times bigger than we can observe, maybe much larger. Other estimates look at this differently. A statistical study in 2011 reviewed various space models and their probability based on what we can observe. It decided that the universe is at least 250 times larger than what we can see, meaning it has a minimum diameter of about 7 trillion light-years. Infinity might still be likely, but these numbers are guesses because we only see what's within our cosmic horizon. Everything past that is hidden. We can make guesses based on the consistent patterns we see and what inflationary models predict, but we can't directly verify. The entire universe could be thousands or millions of times larger than we know, or it could be infinite. An infinite universe brings strange ideas. If space never ends, then every potential arrangement of matter must exist somewhere. There'd be infinite Earths, infinite Milky Ways, and infinite versions of every galaxy we see. Probability loses meaning with infinity because everything that's possible happens infinitely. Most space experts believe an infinite universe is possible, maybe even probable. Measurements of the cosmic microwave background suggest that space is flat in geometry. Flat space that goes on forever is the simplest idea that matches the data we have. Other ideas, like space curving around and connecting back to itself, aren't out yet, but need fine-tuning to fit what we see. If the universe is limited in size, we could measure it if we could see past the horizon, but we can't. What we can see of the universe is like a sample, and we need to guess the whole picture from it. It's like trying to figure out an ocean's size by looking at just one drop. The drop tells you what water is like, but not how big the ocean is. Seen this way, the Milky Way seems tiny, just one galaxy out of 2 trillion in what we can observe. That part might be less than 1% of everything, with the whole being possibly infinite. As you scale out, the previous size looks smaller and smaller. But we live where the Milky Way seems big. Light takes 100,000 years to go from one side of the Milky Way to the other. That's way longer than all of human history put together. We evolved on a planet going around a pretty average star in an average spot in just one galaxy. That one galaxy has more stars than we could ever count, and more worlds than we could explore even in a million lives. In our observable universe, there are things so huge, we need new words to describe them. Superclusters, filaments, vast empty spaces spanning hundreds of millions of light years. And this might all just be a small part of something much bigger. The scale is hard to grasp, but a good comparison brings the vast universe back to something familiar to us. Is the universe never ending? This question splits cosmologists, though most evidence points in one direction. Checking the geometry of space using precision measurements of the cosmic microwave background shows it looks flat, with 1% accuracy. Flat, infinite space is the simplest way to see things. An infinite universe doesn't have a center or edge. Every spot is the same. If you traveled in any direction forever, you'd never find an end. Space just keeps going. New galaxies, new structures, new places that are statistically similar to where we are, but unique in specific details, repeating over and over. This leads to the cosmological horizon problem. If the universe is infinite and space is expanding, regions beyond the cosmic horizon have never interacted, but still look nearly the same. The cosmic microwave background's temperature and density are almost identical everywhere. How can unconnected parts be so similar? Cosmic inflation explains this. Before inflation, our observable universe was tiny, much smaller than now. Back then, all parts we can now see were in touch, reaching the same temperature and density through regular physical processes. Inflation then stretched that small even patch into something much larger. The areas lost contact during inflation, but kept their original uniformity. This explanation fits whether the universe is finite or infinite. If infinite, inflation took an already infinite universe and made it exponentially bigger, thinkably possible. If finite, inflation expanded a small universe into a much larger, still finite one. Either outcome still leaves a universe where our observable part is all the same but still represents just a small piece of the whole. Some ideas suggest the universe might be finite yet boundless, like the surface of a sphere. On a sphere, you can go straight in any direction and eventually end up back where you started. The surface has no edge but has a size limit. It's like a 3D shape that lets you travel through space and eventually come back, though the distances are way beyond the part of the universe we can see. This setup needs space to be bent in certain ways. The cosmic microwave background shows us that this bending is very slight. If space wraps around itself, the curve is so mild that the loop is much bigger than what we can see. If the universe is a sphere, it could have a radius of trillions of light years. The curve is too gentle to notice locally. Other ideas suggest a multiverse, where our universe is just one bubble in an ever-expanding space, with other bubbles having different traits, constants, and rules. We live in one bubble that supports life. Beyond our bubble, there are many more, unreachable and unseen. This idea hints that our universe has a limit, while the multiverse is endless. These ideas are speculative, since we can only observe our nearby cosmic area. Whether space goes on forever, loops around, or ends in some way is unknown with today's technology. Future studies might narrow down our options, but it might always be a mystery. Practically, whether the universe is infinite doesn't really matter. What we can see already has enough galaxies and stars to bog us down. 2 trillion galaxies stretching across 93 billion light years are already beyond our understanding. Whether that's everything or just a small part doesn't change what we face. The Milky Way has hundreds of billions of stars. The observable universe has 2 trillion galaxies. If you multiply those, you get at least 700 sextillion stars, each possibly with planets. The chances for worlds, life, and civilizations are mind-boggling. And if the universe is infinite, those gigantic numbers become truly endless. Even with this massive scale, we can understand our place in it. We know our cosmic address and the structure hierarchy, and comparing that to human scales shows how small we really are. Earth is about 8,000 miles in diameter. That feels huge to us, walking on it. Mountains rise thousands of feet, oceans spread thousands of miles, and continents cover half the globe. From our view, Earth feels big. Zoom out to the solar system, and Earth becomes a small blue ball next to the Sun, which is 100 times wider. The distance to the Sun is 93 million miles, so vast that light takes 8 minutes to travel it. The solar system's boundary, where the Oort cloud ends, is nearly 2 light years away. Earth gets even tinier. Zoom out to the Milky Way, and the solar system disappears. The galaxy is 100,000 light years across and has 400 billion star systems. If the Milky Way was the size of North America, the the solar system would be smaller than a grain of sand, and Earth would be invisible under a microscope. Zoom out to the local group, and the Milky Way is one of 3 major galaxies in a space 10 million light-years across. If the local group was the size of North America, the Milky Way would be like the size of a quarter, and Earth would be tinier than an atom. Zoom out to the observable universe, 93 billion light-years in diameter. If you shrank Earth to the size of a virus, around 100 nanometers wide, the observable universe would fit roughly the size of our solar system. A virus compared to the distance from here to beyond Pluto shows the scale between our world and everything we can detect. Another way to see this is by counting every grain of sand on all the beaches and deserts on Earth, which adds up to about 7 quintillion grains, or 7 followed by 18 zeros. The observable universe has around 700 sextillion stars, which is 100 times more stars than there are grains of sand on Earth. Each of these stars might have multiple planets, making the number of worlds beyond comprehension. Looking at time, if we compress the universe's 13.8 billion year history into a single year, the first stars would appear around January 15th. The Milky Way would form by early March, and our solar system would show up on September 1st. Complex life would appear in mid-December. Dinosaurs would walk the Earth from December 26th to 30, and modern humans would arrive in the last 30 seconds before midnight on December 31st. All of human civilization, every empire, every discovery, and every war happens in that last fraction of a second before the year ends. What we think of as ancient history happened incredibly quickly compared to the vast timescales of the universe. Earth is young compared to the universe, existing for only a third of its history. The atoms in our bodies are older than Earth. Carbon formed in stars that exploded billions of years ago, and hydrogen in our water formed just minutes after the Big Bang. We're made of recycled stellar material from stars that died. Each breath contains atoms from distant stars, which shifts how we see ourselves. We are part of the cosmos examining itself. The universe made stars, then planets, then complex chemistry that led to living things and ultimately consciousness, capable of understanding its origins. We are how the universe knows it exists. Despite this connection, the scale difference is overwhelming. Earth, the Milky Way, and even the local supercluster disappear compared to the observable universe, and the observable universe might be just a tiny part of the whole. As we zoom out, the previous scale becomes too small to see. This raises the question that has puzzled philosophers. Why does the universe need to be so big? Light travels at 186,000 miles per second, and nothing moves faster. This speed limit, proven through countless experiments, determines how quickly information can move in the universe and what we can observe. The universe started 13.8 billion years ago. This age is proven through different methods, including measuring the cosmic microwave background temperature, the abundance of light elements, and the expansion rate. Light has only had 13.8 billion years to travel, which limits how far we can see. Even without expansion, this would restrict our observations to a sphere 27.6 billion light-years wide. But as space expands, distances grow while light is traveling, pushing this limit to 46 billion light-years, the current radius of the observable universe. Beyond that point, light hasn't reached us yet, no matter when it was sent. This creates a moving boundary. Every second, light from a little farther away finally arrives on Earth. The observable universe grows by about 3 light seconds per second, or roughly 560,000 miles. In a human lifetime, the observable universe expands by billions of miles. New galaxies become visible at the edge of what we can see as their ancient light finally reaches us. But this won't last forever. The universe's expansion puts a cap on how far we can see in the future, about 62 billion light years. Galaxies beyond that point are moving away so quickly, their light can never get to us. Over time, more galaxies will reach this limit and disappear from our view. Instead of seeing more, we'll actually see less of the universe. In 100 billion years, based on how expansion is going now, people in our galaxy will notice a much emptier sky. Most galaxies will be too redshifted to detect. The cosmic microwave background will cool, and its radiation will be too stretched out for us to observe. Space will seem dark and quiet, except for a few galaxies nearby. Any future civilizations will have no way to learn about the Big Bang. The evidence will have expanded too far away. They'll look at nearby galaxies and see them as gravitationally bound, not expanding, and might think the universe is unchanging and only as big as their local group. They'll miss out on knowing the universe's true nature. This poses a worrying thought. Maybe we're already experiencing this. Maybe important evidence about the universe's beginnings or nature is already beyond our reach. Some big questions might stay unanswered, not because they're too hard, but because the info we need is out of our cosmic neighborhood. We might be clueless about key details. The cosmic horizon also limits our knowledge about the universe's shape and structure. If space loops back on itself, but the loop is beyond what we can observe, we'll never know. If the universe has unusual shapes or repeating patterns that are bigger than what we can see, we remain clueless. Our view is limited, and guessing beyond it might lead us astray. Time also puts a cap on how far back we can see. The cosmic microwave background comes from when the universe was 380,000 years old, when it became see-through for light. Before then, space was a hot plasma blocking photons. We can't see earlier times with light. The first 380,000 years are hidden. Gravitational waves could help us look further back. These space-time ripples pass through matter and radiation without trouble. Waves from right after the Big Bang could still be out there. Finding them would give us a glimpse of those times. But these signals are super faint. We'd need detectors way more sensitive than what we have now. Our view of the universe is limited by time, the speed of light, and how the universe is expanding. We see only a part during a certain time in cosmic history. That part has about 2 trillion galaxies and covers 93 billion light years. It's huge, but it could be just a brief look at something much bigger and more complex than we can grasp. The question is, if our view is so limited, what might be out there? Beyond our cosmic horizon is space we'll never see. Light from there hasn't reached us, and never will, because of expanding space. That space might be like what we observe, following the same rules, filled with galaxies in the same pattern. Or it might be totally different. Some theories even suggest a multiverse. In eternal inflation, random quantum changes cause some areas to stop inflating and create bubble universes like ours. Other areas keep inflating endlessly, constantly forming new bubbles. Each bubble turns into its own universe with its own physical traits. Our observable universe is just one bubble in an endless frothy space. Different bubbles could have different physical constants. Gravity's strength might change. The mass of electrons could be different. The number of spatial dimensions might not just be 3. Most bubbles wouldn't support life because their physics wouldn't allow stable atoms or stars. We happen to be in a bubble where conditions let complexity happen. This idea can be tested. If our bubble bumped into another one in the past, that collision would show up as a big circular pattern in the cosmic microwave background. So far, no clear signs have been found in searches for such patterns. Either there haven't been collisions, or the signs are too subtle for current instruments to catch. Another theory says the universe is cyclic. It expands, then contracts, then bounces into a new expansion phase. Each cycle erases clues of the earlier ones. We are in the current expansion phase, unaware of countless cycles before or after. This idea removes the need for the universe to start from a big singularity and explains why physical constants have the values they do. They change over cycles to create stable universes. The cyclic model faces issues. Entropy increases every cycle, and eventually, the universe might not be able to bounce back. Without a way to reset entropy, cycles need a beginning. That beginning raises the same questions about initial conditions that cyclic models try to avoid. Another bold idea is that the universe is a hologram. All information in a space volume is stored on its boundary surface, like a hologram storing 3D images on a 2D film. In cosmology, this suggests our 3D universe, and everything in it is a projection from data on a 2D surface at the cosmic edge. Evidence comes from studying black holes and trying to mix quantum mechanics with gravity. The math implies reality may have fewer basic dimensions than we think. What we see as 3 spatial dimensions might be a result of something from a lower dimensional system. Tests of this theory look at whether natural processes show signs of a 2-dimensional structure. So far, results are unclear. These theories are speculative. We can only observe our nearby cosmic area. Looking beyond it needs assumptions we can't check. The universe might be a single bubble in an endless multiverse, or it could be everything that exists. It might be cyclic, holographic, or something we haven't thought of yet. Current observations don't tell us which is correct. What we do know is the observable universe has 2 trillion galaxies, each with billions of stars, all spread in a cosmic network spanning 93 billion light-years. That structure formed from tiny density changes in the early universe, boosted by gravity over 13.8 billion years. Dark matter provides the framework. Dark energy speeds up the expansion. Ordinary matter forms galaxies, stars, planets, and eventually life. The Milky Way is just one galaxy among trillions in this vast cosmos. Our spot isn't central or unique. We orbit an average star in an average spot within an average galaxy. But from here, we've mapped the layout of the observable universe. We've traced our cosmic address from Earth to the solar system, to the galaxy, to the local group, to the Virgo supercluster, to Laniakea. We understand the hierarchy. We've realized it might go on forever in both directions. There could be smaller structures inside atoms, particles, and forces we haven't found yet. Larger structures might lie beyond the horizon, patterns we can't see, scales that make superclusters seem like atoms. The universe might be endlessly repeating, with no smallest or largest scale, just levels we can currently reach. Still, no matter what's beyond our view, we can grasp a profound truth about our place in the universe. The Milky Way is 100,000 light-years wide, while the part of the universe we can see is 93 billion light-years across. The whole universe might be infinite. These numbers show our small place in the universe, and it's pretty humbling. We live on a planet that's 8,000 miles across, going around a star which is just one of 400 billion stars in our galaxy. And as our galaxy is just 1 out of 2 trillion, in the part of the universe we can see, what we call the observable universe could be just a tiny bit of all that exists. As we look bigger, the importance of our planet shrinks almost to nothing. But here's the funny thing. Even being such a tiny part of it all, we still get the big picture. Stuck here on Earth, we've mapped out the universe. We've measured how far away galaxies are, even billions of light years away. We've even figured out what happened right after the universe began. It's almost as amazing as existing at all. The universe doesn't have to make sense to us. The rules of physics could have been random or messy and hard to understand, but instead they follow patterns we can figure out. Nature isn't trying to be mysterious. It's like it gives answers if you know how to ask. We learn everything from light. Light particles, called photons, travel huge distances to bring us info about their sources. By studying these photons, we find out what's in the universe, how far away things are, and how it all changes. Light can take billions of years to get to us, but when it does, it tells us stories about galaxies and stars and the spaces between them. We're like archaeologists, digging up the past through the lens of astronomy. The size difference between Earth and the universe is similar to the difference between atoms and us. An atom compared to a human is like a human compared to the Milky Way. We're in the middle, not the biggest or the smallest, able to look in both directions. Being in the middle gives us perspective. We're small enough to stay humble, but big enough to figure things out. Knowing where we are in the universe doesn't really change day-to-day life. Gravity still works, and light still travels. The same rules of physics apply everywhere, from galaxies to falling objects on Earth. The universe works the same at all levels we can see. This consistency hints that the rules we uncover are more than just weird local chances. They're basic parts of reality. It also hints we might not be alone. 2 trillion galaxies with billions of stars mean there are trillions of planets that might have the right conditions for life. The chemistry that makes life uses common elements made in stars across the universe. The same processes that led to life here should happen elsewhere. Whether that life becomes intelligent, we don't know, but there are billions of chances. If there are other intelligent beings, they see the same universe we do, just from their own spots. They notice galaxies moving away, measure cosmic expansion, and find dark matter and energy too. The universe shows itself to anyone who looks carefully. Even if we're too far apart to meet, we're connected by discovering the same things. Our place in the universe is brief and small. We live on a single planet, in a single galaxy, in a tiny part of an endless cosmos. We're temporary groupings of matter that have become self-aware. The atoms making up our bodies were created in stars and will return to space when we're gone. We are the universe, looking at itself, understanding itself, measuring itself. The fact that we can understand even a small bit of the universe around us is amazing. Us being able to ask these big questions is pretty unlikely. The fact that the universe lets us find answers says something deep about how consciousness and reality are connected. The Milky Way is mind-blowingly huge, and the known universe is even bigger. What's beyond that could go on forever, somewhere in all that, on a tiny rocky planet. Creatures have evolved who get just how massive the universe is. Knowing that doesn't change the vastness or make us more important. But it does mean the universe holds meaning because we're here to see it. Even though we're tiny, short-lived, and not especially important, in the grand scheme, we've figured out the big structures around us. We know where we are. We get our place in it all, and this understanding, as fragile and partial as it is, shows how our awareness can stretch across the universe to see the big picture. The observable universe has about 2 trillion galaxies spread across 93 billion light-years. The Milky Way is just one of those galaxies, and Earth is just one planet in it. You live on that planet for only a short period compared to cosmic time. Yet, in that brief time, you can look up, see light that's taken billions of years to travel, and understand how it got to you. That's your spot in eternity.